In this video tutorial, we're going to be discussing composite walls, and we see composite walls in various different building applications. If you think of the walls of a typical house, then you may have plasterboard on the inside, you may have a layer of brick and a layer of breeze block, and quite often there would be a cavity which would either contain air or some kind of insulation. Another example might be a double glazed window unit, where you have glass on the inside, a cavity in the middle, and then glass on the outside. So there's various different applications for these types of calculations within the building services industry. So the example that we have on the screen here is a composite wall made up of 3 layers. The first layer is plasterboard, the second layer is a breeze block, and the third layer is brick. On the inside, or the side where we have the plasterboard, the room temperature is 22 degrees C, and at the other side, the outside air temperature is 4 degrees C. Now, I've also specified that the total area of this wall is 25 metres squared, and what we want to determine is the total rate of heat transferred from inside the room to outside of the building. So in the bottom left-hand corner, I've provided some data. K represents the thermal conductivity, and T represents the thickness of the layer. So for plasterboard, we have a thermal conductivity of 0.1 and a thickness of 12 millimeters. For breeze block, we have a thermal conductivity of 0.4 watts per meter per Kelvin and a thickness of 150 millimeters. And for the brick, we have a thermal conductivity of 0.7 watts per meter per Kelvin and a thickness of 80 millimeters. Over on the right-hand side, we have the formulas that we need to use. The top formula there is for the rate of heat transfer, and we have the hot temperature minus the cold temperature divided by something called the total thermal resistance. Now, when we approach these problems, we need to calculate the thermal resistance for each layer. So we have a formula for that. It's the thickness divided by the thermal conductivity times the area. It is worth mentioning here that all we're considering is conduction through the wall. In a later tutorial, we'll consider convection, and there we need to consider what's happening at the surface of the internal layer here and the surface of the external layer on the outside. So there we'll be looking at how the wall itself interacts with the surrounding fluid. But for now, we're just going to concentrate on conduction. So first of all, we need to calculate the thermal resistance of each of our layers, and then in order to get our total thermal resistance, we just add each of those values together. So let's begin with the thermal resistance of our plasterboard. And we've said that the thickness of the plasterboard is 12 millimeters. Now it's important to remember to work in meters, so 12 divided by 1000 is 0.012. We've specified that we have a thermal conductivity of 0.1 for our plasterboard, and the area of each layer, because it's the area of the wall, is 25 meters squared. Now when we run that through the calculator, we get a thermal resistance for the plasterboard equal to 4.8 times 10 to the minus 3. The units of thermal resistance is Kelvin per watt. Let's repeat that for the breeze block. So R2 then is the thickness of the breeze block in meters, 0.15, divided by its thermal conductivity, 0.4, times the area, giving us a thermal resistance equal to 0.015 Kelvin per watt. And finally, we have thermal resistance of the layer of brick. The brick has a thickness of 80 millimeters or 0.08 meters. It has a thermal conductivity of 0.7, and once again the area is 25. Now that gives us a thermal resistance equal to 4.571 times 10 to the minus 3 Kelvin per watt. Now we have each of the individual thermal resistances, we can find the total thermal resistance, because all we're going to do is add those 3 values together. So we have our total equals 4.8 times 10 to the minus 3 plus 0.015 plus 4.571 times 10 to the minus 3. And that gives us a total thermal resistance equal to 0.024371. And again, that's Kelvin per watt. So the final step then to calculate our heat transfer is to do our hot temperature minus our cold temperature divided by that value of R total. So we have phi equals 22 degrees minus 4 degrees, all divided by 0.024371, giving us a rate of heat transfer equal to 738.6, and the units for rate of heat transfer is watts. So what we have there is the total rate of heat transfer. If we wanted the rate of heat transfer per metre, then all we would need to do is divide through by our area. Now, the advantage of doing that is if we were then to increase the area of the wall, or consider a number of walls, then we could easily calculate the new rate of heat transfer as that area increased. So our rate of heat transfer per metre then is going to be 738.6 divided by 25, which equals 29.5 watts, but it's important to remember to specify that that's watts per metre squared now. So for every metre squared of wall space that we have, we're losing 29.5 watts or 29.5 joules worth of energy every second. Now, if the example hadn't given us an area and had just asked us to calculate the rate of heat transfer per metre squared, then all we would need to do is replace this area here with 1, or in effect it disappears.